is Nguyen, and I'm from Western University. So I held an NSERC USRA at Western University and did research work under the supervision of Ludmila Goncharova and Peter Simpson. So today I'll be talking about my research work on quantum dots. So I'll start off with some background theory about quantum dots, and then I'll describe my experiment, and then present the experimental results, and then end up with conclusions. So semiconductors are materials with electroconductivity that's intermediate between insulators and conductors. So when semiconductors conduct electricity, electrons separate from atoms, leaving behind holes. So after an electron separates from an atom, leaving a hole, this electronic hole pair we could call an exciton. So quantum dots are basically granular semiconductor nanostructures. And in quantum dots, these electrons are not free to move around everywhere, instead they are spatially confined. So quantum dots have useful electronic and optical properties, which provide new grounds for applications in optoelectronics, biology, and even quantum computing. And one emerging application is quantum dots display devices, which emit light with high efficiencies at various wavelengths within and outside the visible spectrum. So all semiconductors have a bandgap energy, which is defined as the energy gap between the conduction and the valence band. So here we have a quantum dot that is spatially confined in 3 dimensions, as shown by these arrows. So similar to how we could define a Bohr radius between an electron and a proton in the hydrogen atom, the exciton Bohr radius is between an electron and a hole. So when the radius of the quantum dot is less than the exciton Bohr radius, the bandgap energy of the quantum dot is inversely proportional to its size squared. And this relationship is called quantum confinement. So a matrix is a material that hosts or contains quantum dots. So the quantum dots I study are made out of silicon. And silicon nitride is a commonly used matrix material to contain silicon quantum dots. So silicon nitride can be prepared non-stoichiometrically, and we term this as Si3nx, and x is the stoichiometric coefficient for nitrogen, and this value could vary. Secondly, they have an amorphous structure, which means that they don't have a consistent crystalline lattice. And lastly, these silicon nitride matrices embed a size distribution of silicon quantum dots. So my project goal is to study the optical properties of silicon nitride that contain quantum dots. So silicon nitride can be fabricated using plasma-enhanced chemical vapor deposition. And in this method, silane and ammonia gases are leaked into a deposition chamber, and electrical discharge is applied to create a plasma where the gases chemically react, and the products are deposited on the silicon wafer substrate. So by varying these gas flows, we could actually alter the stoichiometry of the silicon nitride samples. And so we have a large library of silicon nitride samples. And these samples, some of them I have made myself, and there are samples made by others in the past. So I applied several measurements on these samples. So I applied ionospheric techniques just to determine the stoichiometry. And next step, I followed up with optical measurements. And this consists of photophotometry, photoluminescence spectra, and time-resolved luminescence. And I'll describe these later. So Rutherford backscattering spectroscopy, or RBS, is an ion scattering technique used to determine the elemental composition of materials. And I use RBS to extract the silicon in nitrogen composition. Secondly, elastic recoil detection, or ERD, gives the depth profile of hydrogen. So this allows me to determine the hydrogen composition and allows me to estimate the thickness of these silicon nitride films. So I measured RBS and ERD on a series of silicon nitride samples where the silane gas flow rate was fixed, and I measured the ammonia gas flow rate. And so on this figure, I plotted the silicon, nitrogen, and hydrogen composition as a decimal percentage versus the ammonia gas flow rate. and the ammonia gas flow rate has units of standard cubic centimeter, or SCCM. And we can see that when the ammonia gas flow rate increases, the silicon composition decreased, but the nitrogen composition increased. But however, the hydrogen composition remained roughly constant at about 20%. So next, I took the ratio of the nitrogen and the silicon composition and multiplied by 3. And this calculates the stoichiometric coefficient for nitrogen. And this value plateaus towards 4 as we increase the ammonia gas flow rate. So next, I measured ellipsometry, and ellipsometry is an optical tool used to determine film thickness. So I measured the film thicknesses of these silicon nitrogen samples and compared it with the thicknesses estimated by RBS and ARB. And you can see that they show a very strong agreement. So next, I extracted the refractive indices for a range of wavelengths and plotted it for several silicon nitrogen samples with varying stoichiometries. And you see that when the nitrogen composition in the sample increased, the refractive index decreased. And another way to look at this is just to take a slice at some reference wavelengths. I use 630 nanometers, which is the wavelength of a helium neon laser source. And so I plotted this refractive index at 630 nanometers versus the stoichiometry values that I calculated from RBS and ARB. You can just see that decrease in the refractive index. So next up, I measured photoluminescence spectra. And photoluminescence is a phenomenon where materials will emit their own light after being excited by an external light source. So in quantum dots, an electron absorbs a photon, and if this photon has enough energy, the electron will climb the bandgap energy, enter the conduction band, leaving a hole in the valence band. And so this is the exciton, and there's a Coulomb interaction between the negative electron and the positive hole, which causes the electron to recombine with the hole through de-excitation and emit a photon whose energy is equal to the bandgap energy of the quantum dot. And according to quantum confinement, the bandgap energy is inversely proportional to the size of the quantum dot. So we expect blue or emissions for small quantum dots. And to measure photoluminescence, here a sample is excited with a laser source, and it undergoes the PL mechanism or photoluminescence mechanism that I just previously described. And the sample emits light, which gets focused and travels through a fiber optic cable. And this light gets counted and collected in wavelength channels in that spectrometer. And as a result, we get a photoluminescence or a pale spectrum. And so this is just the light intensity at the wavelengths. So I obtained several PL spectra for these silicon nitrogen samples with various stoichiometries, and they're all at 500 degrees, which optimizes the PL intensity. And we can see this beautiful blue shifting of the PL peaks as the stoichiometry of the nitrogen increase. So next, I plotted the wavelength, peak wavelengths versus the stoichiometry. And to explain this decrease, when silicon nitride has more silicon, it will also have less, when silicon nitride has more nitrogen, it will also have less silicon. And with less silicon, we get smaller quantum dots. So with smaller quantum dots, we expect them to emit lower wavelength PL. And so this is actually strong evidence for quantum confinement in these samples. And studies have shown similar results. And if you notice, there's also a second peak that evolves for samples that contain a higher content of nitrogen. And you can see it up closely here. But studies have also shown that this is due to defects in the sample. So I measured the full width half maximum and plotted the stoichiometry, and so it declines around 4, the stoichiometry relatively 4. And then I plotted the intensity of the peaks versus the stoichiometry, and it peaks around the value of 3. So next up, I measured the time result of luminescence. So here, this laser is controlled by a frequency generator and a power supply to become a pulsed laser source. So when the laser is on, the sample gets excited through the PL mechanism that I described previous slides ago, and it emits PL light, and this PL light is collected by a forward multiplier tube, which converts the light to a voltage. So the input voltage to the laser and the PMT voltage is displayed on an oscilloscope. And you can see here that when the laser is on, or during this pulse, the PMT voltage saturates, and because the PL activity reaches a maximum in the sample. But when the laser shuts off, the sample undergoes de-excitation, and the PMT measures this as an exponential decay process. So I measured these PL decay curves for the same silicon nitride samples that I obtained the spectra for. And here I plotted and these curves are plotted on a normalized voltage and time grid. And you can see that for samples containing more nitrogen, they actually show longer lifetimes. So in conclusion, I determined the stoichiometry of silicon nitride samples, and then I applied a series of optical measurements just to show that there's stoichiometry-dependent variations in the optical properties. And the highlighted result is the PL blue shifting, and this actually provides evidence that quantum confinement occurs in this system. And further, I want to do further investigation on these results. In particular, we want to apply quantum confinement theories and models to see how well it fits with the data. And this will help us establish our understanding of the fundamental physics of how quantum dots work. So thank you for listening to my talk. I hope you enjoy it. Are there any questions?
How can you say that it's from defects? How do you know for sure that those?
Oh, so we could apply other optical measurements like FTIR, the Fourier transform method, and this will determine what sort of bonds are in the silicon nitride films. So we determine silicon to nitrogen bonds, silicon to hydrogen bonds, and these are responsible for making up the defects.
So what is it that defines the size of your quantum dot? Is it the stoichiometry? And if so, like, do you have like an image in your head? Because I can't really picture how more nitrogen would mean smaller or bigger quantum dots.
Yeah, the fact that you have a deficient amount of silicon, smaller quantum dots will nucleate, should nucleate. So, and that's why we see the lower wavelength emissions. And in order to actually determine these quantum, like whether these quantum dots shrink with the stoichiometry, we need to actually take imaging of the samples. We need to actually see images of the size distribution of the quantum dots inside the film. But right now that's too expensive, and we're waiting to take images of these samples just to see how they look like, and we can actually measure the size of the quantum dots.